Okay. So with this, single phase circuit is over, right? So my suggestion is you follow some your what you call some good books for solving numericals, right? And next we'll come to the three phase circuit. So generally power generation in three phase circuit, nothing will be told here, just giving you some flavor, because our objective is to study the three phase circuit analysis. So generally your what you call that a simple your what you call three phase generator, we call alternator, has been drawn here, right? So suppose this is suppose for example, for your understanding, suppose this is a magnet, right? And magnet is rotating, the direction of the rotation is given this anti-clockwise direction, it is rotating, and magnet is surrounded by, right, magnet is the you are surrounded by that your some your what you call say three phase your that three phase winding we call, right? So your what you call, and these windings are called your what you call this is we call the static. This is this rotor actually rotating, this magnet is rotating, we call this is rotor, this name is rotor, right? And surrounded by some windings, we call it is static, we call it is stator. So question is that generally suppose this is for conductor A, suppose if you take a page, if it is current entering into this, then at A dash it is leaving. Similarly for B also, B dash, and similarly for C dash, right? So this physically these windings are 120 degree apart, right? So total is 360 degree. Similarly A dash, B dash, and C dash, basically physically they are 120 degree apart, right? Now question is that, so this is a rotor, is surrounded by a static part called rotor, and this static part, that winding are placed 120 degree apart, right? But as it is revolving, the magnet is revolving, there will be flux linkage, that your what you call in this your three different windings which are placed 120 degree apart, right? Because of that output, that your what you call the voltage will be induced in this winding. So you have a magnet, say suppose it is revolving, right, and it is surrounded by your static part called stator, and everywhere that windings are there, that A dash, B dash, and C dash, and these windings are 120 degree your physically 120 degree apart, and when it is revolving means this your what you call that flux linking all these three windings which are placed 120 degree apart, therefore voltage will be induced. So that's why if you look into that, from A dash a terminal is taken as A, this is the it is leaving, if A is entering into that page, and therefore A dash is leaving the page, right? I mean if it is entering, it is leaving, right? And similarly for B dash, if you look, if terminal is taken B, and for C dash it is taken C, this is C dash, it is taken C, right? And another C, if you see A, then your B, and then your C, all these three are branched together, and it is a neutral is formed, right? So this is called neutral point, and all three are branched together and a neutral point is formed, and this is ABC, the three terminals, right? So this is a three phase generator, and sometimes we call it is your what you call it is alternator. So this is, it is synchronous generator. Main thing is that philosophy is different. Just to start the three phase circuit, that is this rotor is a magnet, say suppose it is revolving, and you have windings which are 120 degree apart, right? So as it is magnet is revolving, that means flux linking this your what you call this windings, so voltage will be induced, right? So this is your that means as it is 120 degree apart, how this happened, right? So let me just let me make it this thing. So in this case, if you look into that voltage VAN, VBN, and VCN is taken. So here we have marked that your A, B, C. So one voltage will be A to N, then another will be V to N, another will be your C to N. So VA to N, VB to N, and VC to N, right? So AN, BN, CN we will come to that, we will call it is a phase voltage. So what will happen if we follow the your what you call the this VAN, then VBN, it is moving like this anti-clockwise direction, right? So VAN, so it is your what you call it is moving like this. Then VBN, it is, I told they are 120 degree apart physically, right? Then it is VBN will start from here, and VCN, of course it will come like this, but VBN and VCN. That means VAN is leading VBN by 120 degree, VBN your leading VCN by 120 degree. In other way, VBN is lagging from VN by 120 degree and VCN is lagging from VBN by 120 degree, or VCN is lagging from VN by 240 degree, because this VN is reaching its peak fast than VBN, right? So VN is leading VBN, VBN is leading VCN, and angle is 120 degree apart, right? A, B, C, these are your what you call 120 degree apart. We assume that our VN is the reference based on that, and this is your omega t, and this is the voltage, phase voltage, right? So this is that sinusoidal representation of VAN, VBN, and VB. Only one thing I tell, when you say AN, you take A terminal is positive and N terminal is your what you call negative, right? Instantaneous polarity, instantaneous polarity. So in this case, your 120 degree apart from each other, this phase sequence we call ABC phase sequence, right? We call ABC phase sequence. If you want to make ACB also, it can be done, but phase sequence is ABC. Later we will see that, right? So if it as it is shown that a neutral is formed, suppose if it is a star connected, that means just I told you, whenever you write VAN, that means this voltage actually VAN, right? When I make arrow means it is plus, and instantaneously this is minus. So that's why this is plus, this is minus. Similarly, when you take VBN, so it will be VBN, right? This is my arrow. So B plus, this is your minus. Similarly, my VCN, so VAN, VBN, VCN. So here it is your what you call, this is my VCN, right? So arrow means positive, nothing is shown means it is negative, right? So VAN, VBN, this is figure 3. So this is voltage VAN, this is VBN, and this is your VCN, right? So that means basically what you have a magnet, it is rotating, and it is surrounded by a static part that is called stator, where windings are placed 120 degree apart, right? 120 degree apart. As the magnet is rotating, right? So voltage will be induced, your what you call, in all these 3 different coils which are 120 degree apart, right? Physically it is apart, right? And if you take for example voltage induced in Vn as a reference, then VBN lags from Vn by 120 degree and VCN lags from VBN 120 degree, otherwise VCN lags from Vn by 240 degree, right? This is the philosophy. So this is that this is your, we call, this is your star connection, right? Like a star delta formation you have seen, no? This is also star, but as is AC, one neutral is there. It may be there, may not be there, but here it is. The N is called the neutral point. We will come to later. So now this is actually star connected source. If source is star connected, right? But if it is a delta, there will be no neutral. If it is a delta, if the source is delta connected, right? Now look into that. In this case, there is no neutral. In this case, VAB, right? If VAB means this, when you say VAB, that means A is instantaneous polarity, A is positive, right? And your B terminal is your negative, right? It is negative. So that means when it is VAB, look, this is positive, this is negative, it is VAB, you can write VAB. Arrow means positive, and here no arrow means negative. Similarly, VBC, right? So VBC means there should not be any confusion. When you say VBC, that V should be positive. So here I write it is VBC, so it is plus, it is minus. It is instantaneous polarity. Here it is VAB negative, here it is VBC positive, it is instantaneous polarity, right? So no, there should not be any confusion. Another is VABC, VBC, another is VCA. When you take VCA, this is my VCA, so this is my C, this is positive, right? At that time it is negative. So whenever we say VAB, will A positive, B negative. VBC means B positive, first one is positive, second one is negative, right? This is instantaneous polarity, and this is actually your what you call that 3-phase, your delta connected source, because this is delta connected and this is your delta connected source. That was star connected and this is delta connected, right? So let me clear it. So this is figure 4. Now, so VN, voltage between line A and neutral line N, right, neutral line N. This I told you. Similarly, VBN, voltage between line B and neutral line N, and VCN, voltage between line C and neutral line N, right, AN, BN, CN. Therefore, VAN, VBN, VCN, they are called phase voltages. That means in line to neutral, it is phase voltages. In your residence, whatever voltage you get, basically it's a phase voltage. Like you get 220 volt or so, right? In line to line is different, and that whatever in your residence, in house you get, that is basically phase voltage, line to neutral, right? So VAN, VBN, VCN are called phase voltages, right? Now, if the voltage sources have the same amplitude and frequency omega and are out of phase with each other by 120 degree, the voltages are said to be balanced. That means these voltage sources, they have the same voltage magnitude and the frequency, and their 120 degree phase shift, phase difference between them is exactly 120 degree. At that time you can tell the voltage are balanced, right? If it is not, if one of them is different, then it is unbalanced. But we will study only balanced thing for this course, right? So this implies that if it is so, that VAN plus VBN plus VCN is equal to 0. This is a phasor quantity, right? I will show you why it is 0. If you do it, it will become 0. VAN plus VBN plus VCN is equal to 0. This is equation 1. That means if for balanced voltage, magnitude VAN is equal to magnitude VBN is equal to magnitude VCN, right? These are magnitude. When I am putting mod, these are magnitude, right? Now, if we draw the phasor diagram, then VAN is the reference one, so we call this is the phase frequency ABC. So because B lags from A and C lags from B, so phase frequency ABC, right? So when it is VAN, we write VAN is equal to VP angle 0 degree. This is reference, and VP is equal to my phase voltage. P actually suffix we call phase, so it is phase voltage magnitude, and its angle is 0. This is VAN. Now VBN actually, and all these things, your basically this one is equal to VP. All magnitudes are same. This is VP. This is called phase voltage, right? So in this case, your VAN is equal to VP angle 0 degree. Therefore, VBN is lags from VN by 120 degree. So VBN is equal to your VP angle minus 120 degree, right? Because all magnitudes are same. Then VCN will be, this is my VCN, this is my VCN, this is my VCN, right? So this is my VCN, this angle is 240 degree. So VCN lags from VN by 240 degree. So therefore, let me clear it. Therefore, this one, your VCN is equal to VP angle minus 240 degree is equal to, you can say, VP angle 120 degree. Otherwise, this VCN, this is lagging by 240 degree, or VCN leading this VN by 120 degree, because VCN leading VN by 120 degree. So that means your this one you can make VP angle 120 degree. If you have any other thing, if you have that is your what you call, that is your philosophy, right? So VP angle minus 240 degree, suppose it is multiplied by 1, so it is 1 angle 360 degree. If you add these two, it will be VP angle 120 degree. So basically VCN leading this one by 120 degree, right? So anyway, so this is your VP is equal to 120 degree. VP is effective or RMS value of the phase voltage. Here we are not taking at present any sin omega t or cosine omega t, so it is RMS value of the phase voltage. So whatever we say, VP is the phase voltage, these are all RMS value, right? Everything is RMS value. Now rotor rotates in the clockwise direction. In this case we have taken, say, VAN, then C, and then B. This is phase ACB sequence. If it is ABC sequence was ABC and ACB sequence is ACB. Here it is showing, just here we have taken the convention, it is anti-clockwise direction, rotor rotating. But in this case, if we take in this your what you call, in this case rotor rotating in the clockwise direction, that means this way, omega, right? So this is A, C and ACB sequence, right? So this way little bit you have to keep it in your mind. So now therefore VN is equal to VP angle 0 degree we got, VBN VP angle your 120 degree, For this case, ACB sequence and VCN is equal to VP angle minus 120 degree. This is for your ACB sequence, same as before, only one thing is changed. Now, from equation 1, VAN plus VBN plus VCN, VAN is equal to VP angle 0 degree plus VBN is equal to VP angle minus 120 degree plus VP angle 120 degree. If you just simplify, it will be 1 minus 0.5 minus j 0.866, then minus 0.5 plus j 0.866. It will become 0. So, for balanced source, VAN plus VBN plus VCN must be equal to 0. If it is unbalanced, it may be 0, it may not be 0, right. 0 doesn't mean your what you call that it is your what you call 0 doesn't mean that it will become balanced, because the parameters are taken in such a fashion. Suppose this has become your what you call this 0, right. But for the sake of your understanding, at this stage you just assume that your if this is 0, then your what you call for balanced voltage source VAN plus VBN plus VCN is equal to 0, right. So, now question is that your that is your star connected load. This is whatever we saw, this is for star or delta connected source. Now we will see the star connected load, right. So, in this case your what you call this is I have made it a star connected load. This is Z1, Z2, Z3, and star connected load, it will be balanced and phase A, B, C is given. This neutral dash line is given. It may be there, may not be there, right, may be there or may not be there. So, in that case what will happen, this one actually just 1 minute, this one actually for balance case it is your what you call, it is your always 0. In the case of current it is different. So, in this case for balance case this is actually 0, right. So, now question is that A, B, C, this is your dash line, this is neutral may be there, neutral may not be there. So, this is Z1, Z2 and Z3, this is figure 7. So, for balance for star connect, this is for star connected load, this is star connected. In a DC circuit we have studied star connected, and this is your delta connected. It is your ZC, ZB and ZS. So, star delta transformation same as DC circuit. There it was resistance, here it is impedance, right. And here also A, B and C all are marked. So, this is delta connected load. Now, for balanced load, phase impedance are equal in magnitude and in phase, right. That means your Z1, Z2, Z3 all will be same their magnitude and same angle, right. Then it is balanced. Similarly for here. So, that means your for a balanced star connected load, say Z1 is equal to Z2 is equal to Z3 is equal to ZY, that is Z star, right, we call ZY. For a balanced delta connected load, ZA is equal to ZB is equal to ZC is equal to Z delta equal. We will consider only balanced thing. And star delta transformation or delta Y transformation, the way we have made it for DC circuit, same way you do it, you will get that if Z delta will be 3 ZY, right, or ZY will be 1 by 3 Z delta. Same way you do it, you will get it, right. So, not doing further, because everything have been done for DC circuit. So, same philosophy, only there is a resistance, here it is impedance, right. Take a small example. Determine the phase sequence of the set voltages. VAN is given 200 cos omega t plus 10 degree, VBN 200 cos omega t minus 230 degree, and VCN 200 cos omega t minus 110 degree, right. So, if you draw the phasor diagram, right, suppose this is your reference point. So, VAN is equal to your 200 angle 10 degree, right. It is given your 200 angle 10 degree. Our whether it is cosine also basically nothing but your sine term, right. So, it is sine 90 degree minus theta cos theta, or cos 90 degree minus theta sine theta. So, there should not be any confusion, right. So, here it is your reference line. So, VN if you draw 10 degree, and with respect to that, if you draw the reference, VBN is 110 degree, because it is your what you call, sorry, VCN is given 110 degree and VBN is minus 230 degree, and this is with respect to reference. This is, if you see, this is your 100, your this is your 2, I mean this one is your, with respect to this is your 230 degree, right, from with the reference. Now, if you see the angle between A, B and C, so angle between VN and VBN 110 and 10, 120 degree, this angle is 120 degree, right. Now, if you look into your what you call this C and B, you will get 120 degree. Here also between this is 120 degree. That means your phase sequence is ACB, right. So this phase sequence is your ACB sequence, right. This is whenever apart from 0, 120, if it is given like this, you take a reference, and after that you please draw the phasor diagram, then you will get this. This is ACB sequence. Now balanced star-star connection, balanced star connected source and balanced star connected load. When source is balanced, I mean we will do throughout this course balance only. If unbalanced anything is there, I will tell you, it is balance only. So balanced star connected source and star connected load. Suppose this is my star connected source and this is my star connected load, right. Here also neutral is there, and these two are say connected, no element other things are connected here, and current to the neutral is IN, right. And this is your VAN, VBN and VCN, everything is given, and this is ZY, right. This is small ABC, this is capital ABC, this is the source and this is the star connected load, because it is three phase, right. And current to this, it is IA, this IB and IC, and to the neutral connected, current flowing to this wire is IN, right. So if you now this is the philosophy, this is the circuit, right. So now this one is just, if we draw only the source side, this is figure 11 I am on. If you draw only the source side, this side only, right. So I am not showing any neutral or anything. First let us see the source side, no neutral, nothing is shown, but this wire nothing is shown, only AN is here. So the way I told you, VAB, A is positive means B negative, VBC and VCA, right. So it will be your what you call, that is your ABC is drawn, right, ABC is drawn. So VAN your is equal to VP angle 0 degree, it is balanced. VBN is equal to VP angle minus 120 degree, ABC sequence, and VCN is equal to VP angle 120 degree, right. And this is your AN, that means your this voltage. Suppose if we make like this, this is my VAN, this is my VBN, VC and VCN. Now if you apply KVL, like this, if you apply KVL like this, right, in this mesh, if you apply KVL, it will be VAB moving like this, plus is encountering first, right. Instantaneous polarity is marked VAB plus VBN minus VAN is equal to 0, right. That means my VAB is equal to VAN minus VBN, right. That is VAB is equal to VAN minus VBN. That means your what we call this voltage A to B, we call line to line voltage, because this is line, this is line and this is also line. So A to B is a line to line voltage, right. And when you call VAN, VBN, VCN, it is line to neutral, that is the phase voltage, and this is called line to line voltage, VAB, VBC, VCA. Similarly, other two meshes you can create and you can apply the KVL. So in this case, the way what I wrote, that VAB is equal to VAN minus VBN. So this one, that VBN is equal to, you can write your what you call minus VNB, right. Just you are changing your what you call N to B, right. It is VBN, you can write minus VNB, that's why this is VBN is equal to written minus VNB, that is positive, right. I mean, suppose if your phasor, if your notation is a VBN in this side, suppose this is the point, if you want to make VNB, it will be your VNB, just opposite, 180 degree shift, right. So that's why it is written plus VNB. So let me clear it, right. So that means now my VAN is equal to VP angle 0 degree, and minus VBN minus VP angle minus 120. We are substituting it. If you do so, therefore VAB will be VP, it is 1, angle 0 means cos 0, and this one minus of your cos 120 minus j sin 120, right. If you do so, it will become 1 plus half plus j root 3 by 2, and if you take your simplify it, it will become root 3 into VP angle 30 degree, right. So VAB is equal to root 3 into VP, that means VP is the phase voltage and A to B is the line voltage. So line voltage is equal to root 3 times phase voltage angle 30 degree. Now if you look into this phasor diagram, suppose suppose very simple it is, just have a look, only understanding is required. Suppose this is my VN, this is my VBN, this is 120 degree apart. So this is VBN. So if you make 180 degree other side, this is my VNB, this is my VNB. Whatever I told you just now, this is my VNB, and their magnitude VNB, actually magnitude VNB is equal to VP, VN also VP, and VBN also magnitude VP, right? This is magnitude. So whether you take this direction or that direction, immaterial. So magnitude is VP. So this is, so that means this voltage magnitude is VP, and this one with parallel to this, you draw it here. This is also VP, right? So that's why it is drawn it here. Dash line it is shown. So in the, now I am clearing it. So this angle is that your what you call, now whenever you draw this parallel and make this resultant one, this will be your VAB. Whatever we have got it here, this will be VAB. So VAB is equal to VAN plus your VNB. We should know VAB is equal to VAN plus VNB, right? So here, that's why here we have made it, no, here we made it VAN plus VNB here. So that means if you now take the projection of this one, because this is VP, this is VP, so basically it will be VP cos 30, this angle is 30 degree then, right? So VP cos 30, and this is also 30 degree, so VP cos 30, it will be 2 VP cos 30. I mean this from here to here VP cos 30, from here to here also VP cos 30, so it will be 2 VP cos 30, that is magnitude of VAB will be root 3 VP, and this angle is your 30 degree, right? That means so whatever we did it just now, so that means that line to line voltage magnitude will be root 3 times phase voltage magnitude. Similarly for BCCA you will get similarly, only make 120 degree phase shift, right? Then if it is VAB like this, then VBC will come here, VBC will come here, because this angle to this angle is 120 degree. The VBC is lagging from VN by 90 degree, because this angle is 90 degree, right? So that means whatever you did here, that your VAB is equal to root 3 VP angle 30 degree. This is using this phasor relationship, and this is from the phasor diagram. Both are same, right? So all angles, everything is marked, right? So all angle here it is 60 degrees marked. So this is your 30. This is understandable from simple geometry. It is understandable. So now similarly, VBC also you will get VBN minus VCN root 3 VP angle minus 90 degree. If you do so, same way you will get it. Similarly, VCA is equal to VCN minus VN. You will get root 3 VP minus 210 degree. You just do it, you will get it. One I showed it for you. Other two you please do it following the same thing. It is simple thing. Now if you draw the complete phasor diagram, your phase voltage and line voltage, now look into this, right? So I told you that VAB, VBC, VPC, VCA, their phase difference will be 120 degree, right? But so that's why this is VAB, this is VBC, this is VCA. So AB to BC it is 120 degree, then BC to CA it is 120 degree, and CA to AB it is 120, your what you call 120 degree, right? So now, but VAN to your what you call, and VBC, angle between VBC and VAN, it is 90 degree, right? And all angles are marked, right? And angle between VBN and VBC, it is your 30 degree again, and angle between VC and V 30 degree. So AB and AN, if you look AB and AN 30 degree, if you look BC and BN 30 degree, and if you look CA and CN, it is 30 degree, right? So same philosophy, VAB leading VN by 30 degree, VBN your what you call your VBC leading VBN by 30 degree, and similarly your VCA leading VCN by 30 degree, right? So just you superimpose and just draw this phasor diagram. So this is line to line voltage, and this is your line to neutral, we call phase voltage, and line to line voltage is equal to root 3 times the phase voltage, right? So line voltage sometimes we make VL, sometimes we call, sometimes we write your VL line to line voltage. Some book they may write VLL line to line voltage. It is correct, right? But here we have made it your what you call your VL is equal to magnitude of VB, magnitude of VBC, all are same, magnitude are same, it is balanced. Similarly, line to line current IL is equal to IA, IB, IC magnitude is equal to phase current. Why line current? for this case line current is equal to phase current. Why? The question is that it is star connected load and star connected your, we will coming to this diagram, the star connected load and star connected source, right. So this current is going to the line, we call line current, and this is your, this side is AN, BN, CN, this is the phase impedance of the star connected load. So same current is going here, same current is going here. Similarly for the, similarly from IB also, and similarly for IC also, IN also. If we apply here at this point, if we apply KCL, it will be IA plus IB plus IC plus IN is equal to 0, right. So same current is flowing here, and this is the line current, this is the current from here to here, this is the line, A to A is the line, line to line, this small a to A is line, small b to B is line, small c to capital C it is line, all these cases. So this is line current, same current here is entering into this phase impedance A to N. So that's why line current is equal to here phase current, both are same, right. Hope this is understandable to you. When you will go through this, also consult with some good books, all reference books are given, right. So in this case, so it is line current magnitude is equal to, we are right, is phase current here. So line current is equal to phase current magnitude, right, and line voltage is equal to this one, magnitude VAB, VBC, VCA, they are all same, and line magnitude of line current is equal to magnitude IA, IB, IC is equal to the phase current. I told you for star case line current is equal to phase current, right. Now line voltage leads their corresponding phase voltage by 30 degree, that also we can see from their phasor diagram, right. And from figure 10, that means your if you come to figure 10, here it is, from here it is, right. That means from figure 10, one I am writing, other side show. From figure 10, this current is entering here IA, and voltage here it is VAN, right. That means my IA is equal to my VAN, right, divided by Z star, that is ZY. This is my your what you call V, because voltage here is a VAN, so VAN upon ZY, and this VAN is equal to, this VAN is equal to, nothing is there here, it is simply nothing is there, is equal to your V small an, this one, this voltage, because no element is connected here, so VAN is equal to this VAN, that is this one you can write VAN by Z star, ZY, right. Similarly for IB and IC. So we'll go back to that. So here we are writing from figure 10, IA is equal to VN upon ZY. I told you is equal to VN is equal to VP angle 0 degree by ZY is equal to VP upon ZY, right. So similarly IB is equal to VBN upon ZY, VBN is equal to VP angle minus 120 degree divided by ZY, and VP upon ZY is equal to IA, this VP upon ZY is equal to IA, right. So this VP upon ZY is equal to IA you put, so IB is equal to IA angle minus 120 degree. Similarly, IC is equal to VCN upon ZY is equal to VP angle 120 degree upon ZY, and VP upon ZY is IA, so IA angle 120 degree, right. Therefore, IA plus IB plus IC is equal to IA plus IA angle minus 120 degree plus IA angle is equal to 0, right. Also, IN is equal to, if you apply KCL or what you call KCL, you will get IN plus IA plus IB plus IC is equal to 0. But IA plus IB plus IC is equal to 0. So therefore, for balance case, IN is equal to 0. No current is flowing through the neutral, right. So this is the simple philosophy for three-phase circuit. So this is the summary. So this is the connection star, this phase voltage slash current given. So this is the relationship whatever we have made for star line current is equal to phase current. Line voltage and current, VAB is given, VBC is given. This is the summary, sorry, and IA, IB, IC all given, and this is also given, right, VAN, VBN, VCN, and for star line current is equal to phase current, right. Thank you very much. We'll be back again.